Hello everyone. Today I would like to discuss a crucial concept in machine learning, dimensionality reduction, focusing on one of the most popular and widely used dimensionality reduction techniques, which is principal component analysis, commonly known as PCA. Now, here is an overview of the contents covered on the mentioned topic that includes introduction to dimensionality reduction and PCA, dimensionality reduction techniques, PCA versus high-dimensional data, how does PCA work, applications of PCA, benefits and drawbacks of PCA. Now, let us get a brief idea on dimensionality reduction and PCA. Dimensionality reduction refers to the process of reducing the number of features or variables in a dataset while preserving the important information. In other words, it simplifies the dataset by transforming it into a lower dimensional representation. On the other side, PCA, or Principal Component Analysis, is a statistical unsupervised technique that aims to transform high-dimensional data into a set of lower dimensional components called principal components. It captures the essential patterns and relationships present in the data, preserving maximum information as possible. Here are a few categories of dimensionality reduction techniques. The first category, feature transformation, includes both linear and nonlinear methods. The linear methods are, for example, PCA, principal component analysis, LDA or linear discriminant analysis, truncated SVD, etc. Nonlinear methods include kernel PCA, isomap, TSNE. The feature selection category has filter methods that include chi-squared test, for example, wrapper methods that include forward selection or recursive feature elimination, etc., and the embedded methods that include random forest or ridge regression, etc. PCA versus high-dimensional data. In many real-world scenarios, datasets can often be high-dimensional, meaning they contain a large number of features or variables. While having a rich set of features can provide valuable information, it can also introduce various challenges. Firstly, as the number of features increases, the complexity of the dataset grows, making it more difficult to analyze and interpret. Additionally, computations become more expensive, requiring substantial resources and time. Moreover, high-dimensional data can lead to overfitting, where a model becomes too specialized to the training data and fails to generalize well to new data points. To address these challenges, dimensionality reduction techniques are employed. Principal component analysis is one such technique. It plays a pivotal role in dimensionality reduction due to its ability to capture the most significant variations and relationships within the data. By identifying the principal components which are orthogonal to each other, PCA enables us to represent the data in a more compact form, effectively reducing the dimensionality while retaining crucial information. Now, how does PCA work? Here's a step-by-step explanation of how PCA works. Data preparation. PCA begins with a data consisting of numerical variables. It is essential to standardize the variables by subtracting the mean and scaling by the standard deviation to ensure all variables are on the same scale. Covariance matrix calculation. In this step, we calculate the covariance matrix of the standardized data. The covariance matrix represents the relationships between variables and indicates their degree of linear dependency. Eigendecomposition. In this step, the covariance matrix is then decomposed into its eigenvalues and eigenvectors. Now, eigenvectors are the directions in which data varies the most, and eigenvalues represent the amount of variance explained by each eigenvector. Principal component selection. The eigenvectors with the highest eigenvalues, also known as principal components, capture the most significant amount of variance in the data. These principal components are selected for further analysis. Recast the data along the principal components and axis. In this step, which is the last one, the aim is to use feature vector formed using eigenvectors of the covariance matrix to reorient the data from the original axis to the ones represented by the principal components. The number of principal components chosen determines the dimensionality of the reduced dataset. Let us assume that the scatter plot of our dataset as shown in the diagram. Can we guess the first principal component? Yes, it's approximately the line that matches the green marked line because it goes through the origin and it is the line in which the projection of the points, red dots, is the most spread out. Or mathematically speaking, it is the line that maximizes the variance, that is the average of the square distances from the projected points to the origin. PCA, since it determines its components through the greatest variance by some scalar projection of the data, comes to lie on the first coordinate called the first principal component. Similarly, the second principal component is calculated in the same way with the condition that it is uncorrelated with the first principal component, that is, it is perpendicular to the first principal component, and that it accounts for the next highest variance. This continues until a total of n principal components have been calculated, that is equal to the original number of variables. The scree plot tells us the proportion of variance explained by each of the principal components in a example dataset. On the other hand, the superimposed line chart gives us the cumulative sum of explained variance up until nth principal components. Ideally, we want to get at least 90% variance with just 2 to 3 components so that enough information is retained while we can still visualize the data on a chart. Looking at the chart, I we would feel comfortable using two principal components since the first two principal components almost capture 90% variance in this dataset. Applications of PCA. PCA has found applications across various domains, including image processing, bioinformatics, finance, and more. Its versatility and effectiveness make it an essential tool in the data scientist's arsenal. Here we will be discussing on the three major applications of PCA. The dimensionality reduction for visualization purpose. PCA can be utilized to visualize complex datasets in a lower dimensional space. By reducing the dimensionality of the data, it becomes possible to plot the observations on a 2D or 3D scatter plot, enabling visualization inspection of patterns, clusters, and relationships among the data points. Image compression. PCA can be employed for image compression by reducing the dimensionality of image data by selecting a subset of principal components which capture the most significant image variations. It is possible to represent the image with fewer coefficients while preserving the essential features. Noise reduction in data. PCA can help in filtering out noise from data. The principal components associated with low eigenvalues often represent noise or uninformative variation in the data. By discarding or reducing the influence of these components, PCA can effectively denoise the dataset and enhance the signal to noise ratios. Benefits and drawbacks of PCA. The benefits of PCA includes by reducing the dimensionality. PCA reduces the computational resources and training time required for machine learning algorithms. The reduced feature space leads to faster computations during training, evaluation, and inference stages. Improved interpretability of PCA. It transforms the original features into a new set of orthogonal features known as principal components, and these components can be interpreted as directions of maximum variance in the data. The reduced dimensionality and interpretable components enhance the understanding and interpretability of the data. Thus, it makes it more generalized and human understandable. PCA enables data visualization reducing high dimensions. PCA addresses multicollinearity by transforming the original features into uncorrelated principal components, reducing redundancy and impact of multicollinearity in the data. PCA is a linear dimensionality reduction technique that captures the maximum variance in the data by finding a linear subspace, although it also works for few nonlinear distributed data also in fewer cases. The drawbacks of PCA. There are few drawbacks of PCA since PCA is a linear transformation, so in and of itself does not alter distances, but when we start removing dimensions, that is the principal components, the distances get distorted. This is one of the few drawbacks of reducing dimensions with PCA, and we need to be aware that, especially when working with Euclidean distances based algorithms. That's all. Thank you all.